power and root functions. So this is a polynomial function, as we worked on earlier in this chapter. A power function is just when you take one of the terms of these things and make it a function. So something like this, f of x equals x to the b. That's a power function. A root function is the same idea, but where it's a root instead of a power. So it's 1 over n, which is the same thing as saying the nth root of x. So this would be a root function, hence the nth root. This would be a power function. Some examples include x squared, x pi, which is just x to the 3.14, x to the 0.4. This is actually a root function because that's less than 1. Anytime it's less than 1, it's a root function. And then x to the root 3, the cube root of x squared, which is also a root function. If you rewrite this as 2/3. But they're also known as power functions. How do these power functions look? A square root function looks kind of like a sideways parabola halfway. And a cube root function looks like the same thing, but the left side goes to the left. And then this is a cube root square, which honestly is on a graph I do that often. So let's graph these. Let's see what happens when we change the power of b. So they want us to graph f of x equals x to the b, where b is 0.3, 1, and 1.7. Now to show it to you the easiest way, I'm just going to use Desmos, so you can really see what's going on. So we're going to do y equals x to the 0.3 power. It's like this. And you can see it looks like a normal square root function. The square root is 1/2 power, so it's 0.3. X to the y equals x to the first. So that's y equals x. It's a graph we all know and love. And then how about if we go a little higher, y equals x to the 1.7. So that's almost like x squared. You can see it's like not clearly not x squared, but it's a little bit getting closer to x squared. So you can see what b does. The higher the b is, the faster it grows. The lower the b is, the slower it grows. You kind of see where when it's a higher b, it kind of curves up. When it's a low b, it kind of curves to the right. Okay, let's move on. Curves down. Applying properties of rational exponents. So they want to simplify each one of these by hand. So the key thing with the rational exponent, an exponent is like this. The bottom is the root, and the top is the power. And when you simplify, you always want to simplify the root first. So when you simplify, you want to do the root first. Simplify first. So for like the one right here, 16 to the 3/4, you want to do the 4th root of 16 for it. So the 4th root of 16, and then take that to the 3rd power. You always want to do root first because it makes it smaller, and then you can just make it bigger afterwards. So it's a lot easier to do. The 4th root of 16 is 2, so we have 2 to the 3rd, which is next one, same idea. Now they already have the cube root in there. So the cube root of negative 64. Well, the cube root of negative 64 should be negative 4. And taking that to the 4th power, which is 256. And then since you have a negative to the even power, it makes it positive again. So we just have 256. Doing the next one, same idea. Now they're giving you a choice here. You always want to do the root first. So remember, do the root, then do the power. So this is going to be the cube root of negative 125. And after we're done with that, we'll square our answer. Cube root of 125 is negative 5. Negative 5 squared is 25. So that's how you do these by hand. You do the root first, and then you do the power. It's a lot easier to make it small than make it big. Writing radicals with rational exponents. So we just want to rewrite these as rational exponents. So we want to write it more like this, and not like this. This is writing as a radical, just writing a rational exponent. So it's the same rule applies. Right? So like I wrote this earlier, k over m. This is the root, and this is the power. So the only thing we generally rewrite is the root. We don't ever rewrite the power. The power stays where it is. So you could write this as the nth root of a to the k power. Right, so notice how the power doesn't change. It always stays in the same spot. It's the root is the one we can rewrite. You could write it as a bottom of a fraction, or you could write it as a root like this. So you look at the first one here. If there's no root on it, it's a root of 2. So this is just saying power of 1 right there, x to the 1/2. Right, you don't see a power in the x, it's a 1. You don't see a root, it's a 2. Next one, just going to rewrite it. The power always stays where it is, and the root becomes the denominator. That's how that one goes. This -5 goes to everything, that's the power. So we just rewrite this as z over 4, because that's what the root was, and then -5 is the power. Now we generally don't want negative fractions, negative powers, so remember what a negative power does. A negative exponent, all it does is flip the base here. So it becomes 1 over z to the 5/4. Right, the only thing that gets flipped is the base, not the actual root. This next one looks complicated. So on the outside is a big old 1/2 power. That's what the root does there. This guy has a power of 1. Power of 1 here, but they're both, that's still 1/3, that's still 1/4. So it's y to the 1/3 times y to the 1/4. Now what this 1/2 power does, it goes to everything in there, so you multiply and multiply. That gets me y to the 1/6 times y to the 1/2. 1/8. 1/8. Right, all you do when you go power to power, you multiply. So 1/3 times 1/2 is 1/6, 1/4 times 1/2 is 1/8. Now I could simplify this, they both go into 24. Right, all we do here is if you're multiplying, you add fractions. Like that. They both go to 24. I can multiply that by this guy by 4 over 4. Multiply this guy by 3 over 3. I get y to the 4 over 24 plus 3 over 24. And I get y to the 7 over 24. That's the smallest I can get it. Okay, next one. Modeling using power functions. So let's bring back my calculator. This time we're going to use an actual TI-84 emulator to model my stuff. So on this, we're gonna model like we did in the past. Now this time we're modeling bird wingspans according to their weights, and they want us to do a power regression. So remember from before, the way we use the regression is stat, edit, and we go through these progressions here. We use cubic, we use linear. This time they want us to use a power regression, which is right here under A. So before I can use that, I gotta type my stuff into my stats. So I'm gonna go stat, edit, and we're going to type in all this information. So here's my x, here's my y. I guess L1, L2, more like it. So it'd be 0.5, L1.5 to 1.5. It froze on me because of course 1.5 to 2.5 and 3. L2, 0.77, 1.1, 1.22, 1.31, 1.4. So it's all in there, and then now we want some power regression, so we're going to quit this, we'll go to stat, go to calculate, go down to power regression. Right, L1, L2 is all good. Frequency list, we're not going to leave that blank. Store request, I will store it. To remember the way the shortcut to do that was alpha F4, and you store in Y1. That's going to store my equation. And there we go. So, A, my power regression is Y equals, now remember, they correspond. A is the coefficient, B is the power here, the exponent. So 0.9674 x to the 0.3326-ish, if I'm rounding it. Right, it's an approximation there. So there we go. Approximate the wingspan for a bird weighing 30.2 kilograms. So they just want to plug this, they just want us to plug 3.2 into this formula here, right? Because kilograms is my x. So we're going to plug in 3.2 for that. Now remember the easiest, so I could just rewrite this and plug in 3.2, not that bad. But since I store requested my equation, the easiest way to do that was to press alpha F4, select your Y1, then parentheses the thing you want to plug in, 3.2. So again, feel free to just rewrite it. You just rewrite input 0.967 to 0.32 3.2.3326. Or you could do what I did and use the calculator information to get 1.4243. So now we're just modeling with power regressions. Now let's talk about how to graph our root functions and our square root functions. So the general idea is here. We're going to talk about two types. We're going to talk about when it's an odd root, and when it's an odd root, what's the key there? You can take an odd like a cube root of a negative. When it's an odd power, you can take the negative. You can take the root of a negative number. That's why you have this like tail on the end right here. So you have the positive side and the negative side, which means my domain is all round numbers. My range is all round numbers. So easy enough to do domain range when it's an odd root. When it's an even root, the problem is you can't take the square root of a negative number, right? The square root of negative 8 is an imaginary number, so that's why there's never a tail on these. So when it's an even root, you only have the right-hand side. And your domain, the way you figure out the domain is whatever is inside that root has to be greater than or equal to 0. So that's your domain. So let's keep that in mind, right? If I give you a root function like this, if n is an even number, then the thing inside of it, ax plus b, must be greater than or equal to 0. That's how you do the domain. But if it's an odd function, the domain is any real number. So let's domain a couple things. So we're going to find the domain of a here. It's an even root, so all I'm going to do is take the number inside of it and set that thing greater than or equal to 0. Because remember, even if we can't take a square root of a negative number, so this must be positive greater than 0. And all we do is solve. 4x is greater than or equal to negative 12, divided by 4. X has to be greater than or equal to negative 3. That is my domain. Any number like negative 3 on is part of the domain. B, it's an odd root. So the domain is all round numbers. Lots of ways to write it. You could write the fancy R, you could write negative infinity, positive infinity. Or you could say all row numbers. But easiest thing to do, right? Find the domain when it's an odd root, just all row numbers. Okay, let's talk about how to graph these things. So normal transformations work, just like in any other graph. If I give you something like y equals a f of x minus h plus k, your starting point is inside opposite, outside follow. So it'd be h and k. And your a on the outside is kind of like the slope. It's not exactly slope, but it's kind of like slope. Right, so you want to treat like a over 1. So your first point is going to be, you're going to go up or down a. And you're always going to go right 1. So whatever so you always put over 1, go up and down that number a, and you always go right 1. Or left 1, depending on what type of graph you have. But the starting point is h and k. So remember, it's called a vertical stretch, but it's treated kind of like slope. So let's do it for a. Y equals the fourth root of 4x plus 12. Square root of 4x plus 12. Now here's the key though. To do transformations, you notice there's no number in front of my x. I gotta get rid of that. I gotta factor it out. So you want x to be alone. I mean, there could be a plus and minus in there, but you don't want you want the coefficient of x to be 1. So you have the factor. So I'm gonna factor out of 4 out of this. I'm gonna get this. Square root of 4x plus 3. Like that. So you factor out a 4 on both of those, piece of the 4 right there. How do I get rid of that? Well, remember you have a radical, you can just pull it out. This becomes this. Square root of 4 times the square root of x plus 3. And the square root of 4 is just 2. So y equals 2x plus 3, radical x plus 3. Right, and that we should know how to graph. Here we're going to start at, my center is going to be, my vertex is going to be inside opposite, outside follow. So negative 3 and 0. And my a is 2. So it's like a slope of 2 over 1. So I'm going to start at negative 3, 0. And then we're going to go up to and over 1. And it looks like a kind of like open parabola, sideways parabola. And that's my basic square root function. And let's do the same thing for the next one. Next one's a cube root. So remember, cube roots look like this. Same idea, but it has a tail on the other end. We're going to treat it kind of the same way. So what was that? The negative 8x plus 8. So y equals the cube root of negative 8x plus 8. Again, I can't have a number in front of my x, so we're going to factor it out. Negative 8, x minus 1, sorry. Remember that when you factor it out, you just divide. So it's negative 8x divided by negative 8, which is 1, and positive 8 divided by negative 8, which is negative 1. And just like before, we're going to split this. Cube root of negative 8 times the cube root of x minus 1. This is just negative 2. Like that. If I want to graph it, right, what is my center? Inside opposite, outside follow. So 1, 0. And my a is negative 2. So a couple things, right? Negative 2, remember that's a vertical shift. It's an open down 2. So it looks different. So let's do like a basic graph just so you can see what it looks like. We're going to go over 1. A normal cubic graph looks kind of like this. So a normal cubic graph looks like moved over 1. But we got to draw negative 2. So it flips and it has a slope of 2. So when you flip it up and down, it means it's going to open like this, right? So this gets flipped to the bottom, this gets flipped to the top. So it's going to be kind of like, start here and go down 2 over 1. So it's going to look like this. And we're going to do the tail on this end. Something like that. This is my answer. And that's the lesson.